My name's Seth Berman. I'm the engineering director at Instantiations, and today I'm going to talk to you about a project that we've been working on for a few years, which is evolving the virtual machine for VA Smalltalk from 32 to 64-bit. So just to kind of frame this talk, it's going to be more about how, originally this product was from IBM, Visual Age, and IBM was a very large team. So we're talking about maybe 40 plus, I don't know, maybe John, is that about right? 40 plus folks on the 60 plus folks on a team developing this product. And then, so at that point, you got a team like that, you've got folks with very specialized skill sets being able to do some specialized things. And of course, the product has transitioned to a much smaller team, yet we still have these big requirements, such as taking a product that, I like to joke that, but it's realistic, that I was in middle school when this project was being started. So I was, yay high. So this is a mature product, and taking something like that with a small team from 32 to 64-bit is with minimal impact, this is the key part, with minimal impact to the customers. Almost sort of like they should just be able to, one day they just walk in, and our goal is to have them launch their existing product on our 64-bit virtual machine. So you roll that all up and you have a very high-risk project. One that almost has the feel of it could be vaporware. It's a very hard project to do. And so this talk is primarily about how we have been successful, and at this part we're so far along that we can almost just claim success. But we shouldn't do that. We're all engineering, know that we shouldn't call that 100%, but it's, for all intensive purposes, it'll happen. So that's what this talk is about, kind of the transition given all those constraints, of which there's a lot. So we're going to talk about, well, obviously with that many constraints, do we really want to do this? So why are we doing this? A little bit about the history, which I've just kind of shared some, but we'll look specifically at some of the technologies that are available historically, kind of the challenges, of which there were many. So how we, with such a high-risk project, how we carried it out. And so if there's time, I'll show a little demo of what we hope the transition will look like for most customers. So first, let's look at why did we do this in the first place? Well, believe me, we'd rather be doing other things, but the kicker is that we have customers who running out of memory. We have customers who are using support from databases or various other libraries that are only beginning to offer 64-bit libraries, which is problematic if you're in a 32-bit application. Sometimes we've got to support folks and tell them, well, there's these workarounds to do it. You can write these wrapper code. It's messy. So it's a big deal to get, as time moves forward, we're just going to see more of that, where you're going to need, 64-bit process. Another point is that our existing VM, it's difficult for us, for some of the reasons I shared with you about the specialization of resources, it's difficult for us to actually maintain and enhance it. Not that it's not good, it's great. It's just that it does require a lot of specialized skills. And because it's been around for so long, it uses a lot of deprecated and obsolete tool chains. So it's hard for us to hook into some of the existing tools. Are you going to ask a question? Or? I can put, let me see if, I'm sure I can kick it up a little bit. Maybe will the slideshow mode work? Does that work better? Okay. So we also have this kind of, the way that the VM is described is in a Smalltalk modeling language, which we'll kind of look at. And again, it's in Smalltalk, and that's really cool. and we think it's neat tech. Unfortunately, it requires, again, a lot of specialization, a lot of upkeep, because we're essentially doing all the backends ourselves. And that's not something that a team of our size really wants to be doing, or should be doing. So basically the goal here in green is to simplify the maintenance and enhancement of the VAST VM, get modern tool chains. And one of the ways we're doing that as well is we're replacing this proprietary modeling language, which hardly anybody understands anymore, minus a handful of us, and replacing it with primarily in C, some C++ now. So let's kind of look at this. What's this modeling language that we use, the Smalltalk generator that generates the VM? So the good news about it, it's really stable. It's basically gone unchanged for 25 plus years. That's a big testament to the folks who designed it. It may be hard to understand. It may require a lot of specialization. But that's a big deal. I mean, that was well done. And but on the other hand, sometimes we may have wanted to create these changes, but just really couldn't. So maybe there's not a lot of bugs, but we also can't really enhance it all that much. So that unchanged in 25 plus years is both good and bad. So it's developed using this proprietary Smalltalk VM modeling language, which is generates the VM. And so essentially what happens is you write the VM code in Smalltalk, described in Smalltalk. It will generate, I mean, it's built on top of this portable assembly layer, which is also in Smalltalk. That portable assembly layer will generate the machine code for the various backends, which you need, if you're going to be doing it this way, you're going to need to know how to gen all the backends as well. So you're basically, you've got the full stack in Smalltalk. So from a technology standpoint, this is really cool. It's a lot of fun to look at and work, and try new things with. But from an engineering standpoint, that's a lot for going to 64-bit VM. Think about all those backends now. That's a big deal for us. That's not something we want to be doing. So so at the end of the day, we've got Smalltalk modeling language. It's obscure. It's really hard to learn. Again, unless you're really specialized, and you can do that. And it also kind of obfuscates the algorithms a lot, and we'll take a look a little bit. It's similar to a kind of a macro assembler. So you basically have a lot of fancy syntax to get the Smalltalk ease of development. But what you really want is the kind of the low-level view, but you can't get at it because you're kind of presented this high-level abstraction, and so it makes it difficult to bounce back and forth. If you have really good tools, that's cool, but we don't. So often we just have to gen the low-level code, and we end up just looking at that. So generating the machine code is a hindrance. So not a lot of we don't have a lot of tooling that can really work with it well. Non-standard calling conventions, standard debuggers don't work. We've got a few tools that we can look at the low-level machine code, but it's not great. It's not a great way to really look at a VM. And the JIT is a hindrance. The JIT is in VM. It's kind of retrofitted into this object-oriented view of a register or of a stack, kind of a register-based stack machine, and it's kind of fit in there, but it's really hard to understand. So that's kind of the takeaway of this whole deal. So this is actually one of the easier ones to read, which is why we put it up here. But this is an example of a primitive written in our Smalltalk modeling language, and so the language itself doesn't describe. So it's not like slang. It's one level down. So it's describing a register-based stack machine. So these kind of in the first four here, we see receiver. I don't know if probably not a lot of people can read it, but basically we're each variable is representing registers. And we're making assignments to those registers. We're testing them. We're doing jumps. Thankfully, the jumps in some of these are abstracted away as Smalltalk, essentially if statements. That's the do. So we can kind of see on this first branch here, we're testing if what got loaded is an immediate, or if it's a byte type of object. If that's not the case, we'll fail, which is a jump, a test and jump, which gets abstracted away because that test and jump gets generated to all the various back-end platforms. So we don't have to know exactly the specifics of test and jump for a specific architecture. We can deal with it this way. So that part's cool. But this is just kind of the way that it ends up looking, and you are dealing at the register level most of the time, which gets difficult when you want to look at algorithms. So here's, we took this, and this is kind of what it looks like in C. It's just simpler for us. We've actually got resources who who are really good at C, who are really good at all the C tooling and looking at it this way. And even for me, I love Smalltalk, and I've had to learn C and all these things, and looking at both, I actually prefer this. So this is kind of what we've gone to for most of the stuff. So challenges. Again, this talk is more about the conversion of, from a large resourced team, a VM, to a small resource team trying to make a huge change like this. So we were first faced with the fact that there were no test cases. The test cases, the VM runs, and we had some various micro S-unit style test cases that came with it, but they were pretty trim. So the real thing is if the image runs, then it must work. So something had to be done about that if we were going to make such a drastic change. One of the challenges is VM and C performance. So the Smalltalk model generated assembly. So the interpreter was very, very fast. It had the JIT. It wasn't built on a C runtime, so it managed its own registers, and it was very, very fast. It remains very, very fast, and so that was hard to compete with going to C. Good news is, we actually have for each bytecode, it's fairly rich, fairly dense. There's actually a lot of stuff we have to do within a given bytecode, and we did find that the C compilers did do a much, much better job generating code as far as reordering. And this makes sense because our existing Smalltalk model was optimized for x86. I mean, this is a long time ago. The deep pipeline architectures that we kind of moved to over time and things of this nature weren't around really then. So the generated code didn't really do a whole lot in that regard. So we had to actually convert a lot of the benchmarks over. We have many, many more now. We grabbed every benchmark we could find, essentially. Toolchain convergence. So we had so a little bit of the existing VM was in C. So we had 4 different compilers for every platform that we used. It was a messy toolchain, really hard to actually just generate the VM. If you made any sort of change to it at all. And so another challenge was just the impedance mismatch of the model versus C-based VM. Model was kind of open-ended in terms of what it wanted to do. It didn't have this C runtime restriction, as I kind of mentioned. So how do we do it? Well, so we moved to CMake and GCC across the board. And so that's on all our AIX, Solaris, x86, and we use register intrinsics for GCC to get the performance back. So we are able, in our interpreter, for example, to make sure that certain important state is kept in registers. And so with that, we are still on a C runtime, so we still lose a register, but we've gotten it back to about 80% of the generated assembler version for the model, which is pretty dang good for a C interpreter. The 64-bit interpreter runs much, much faster, even with all the extra data. Just a lot more registers. And minimal assembler now. With the register intrinsics and some other things we've done, we just have a handful of assembly instructions at the moment. This may creep back up, but we kind of needed to get things under control first. And so really right now it's just for low-level arithmetic and exception handling, and we have this OLE hack to actually be able to communicate with OLE functions, which needs assembly code. So incremental changes, this is the key. This is kind of the key to the whole project being successful, is that we always needed a VM that worked. So we have a working VM, we make a little change, and then, yes.
This is just for my own clarification. So do you mean to say that you have a JIT before, and that JIT was an inference, you removed it, and you put in an interpreter, and
Well, we're going to have a JIT.
the C version of the interpreter runs at about 80% of the speed of the original interpreter?
The originally assembly interpreter, you're right, yeah.
So that would be fair something.
Yeah, so interpreter and interpreter, 80% of the Smalltalk model interpreter, no JIT. Okay, so the JIT, which I'll touch on in a minute, that's the next phase. Yeah, we don't touch. Yeah, our interpreter does not touch the JIT version yet. That's a good question, good clarification. So incremental changes. So in order to do this, remember we're going from a non-managed Smalltalk model assembly, I'll do whatever I want when I want to do it, to something that runs on a C-managed runtime, expects register layouts in certain ways, calling conventions, etc. So that means that as we made these changes, the two are still interoperating. So we had to write shim code so that it could continue to work. So as we bumped it forward, we kind of backported shim code so that the model and the C VM could still stay in sync. And then as we're doing this, we're making the 64-bit clean changes. The detour was from the plan, the interpreter. It didn't make sense to kind of try to interleave it with the two interpreters together. It was just easier at that point, especially this came later when the guys that doing it had very intense knowledge about how this all worked, that they just said, we'll just do the interpreter by itself. We have this feature called just-in-time image conversion. I'll call it an unplanned feature because it was on our roadmap to do, and the guy who did it just came in one day and he said, oh yeah, I did that yesterday. And it's like, okay, I guess we'll just check that off. So basically how this works is that you've got your 32-bit image and image components, which are just this shared memory sections that are kind of in there. They are converted the first time that they're used. And so what this means is that if you load a 32-bit image on a 64-bit VM, it'll on the fly convert it to a 64-bit image. You save the image. Now you got your 64-bit image. That's kind of the end of the story. Now, why is it part of the VM instead of a separate tool? Well, the answer is because part of the VM is to be able to load these 32-bit ICs, which are these kind of the Smalltalk shared library equivalents, shareable pieces of code. You can load those on the fly. And so this is the same piece of logic that does that. So now you can either, when you start up an image, it's the same code that's also responsible for loading these shared modules on the fly. And so in both cases, they'll get converted to 64-bit. So once upon a time, a few years ago at this point, what we started with was the garbage collector. And so we have a scavenger for new spaces and mark compact for the old spaces, and the allocator, which interfaces with it. And so we kind of just converted them one at a time. I converted the scavenger from the portable assembly layer into C. And then I decorated both with bunches of tracing code. And then I would run both, and it would produce millions and millions of lines of tracing, which I wasn't satisfied until they were exactly the same ordering. They don't have to be the same addresses, but they had to be the same order of events that occurred. And so, so this is the kind of incremental change that we worked with. So then Mark Compact came, did the same thing, decorated tracing on both sides, millions of lines of code, everything had to match. And then the allocator, and so it all kind of progressed in that fashion. Unfortunately, so this is the part that we can't do automatically, and this is the fact that the image does have to change. The 64-bitness does show through. However, from the user's perspective, in many cases, they'll never know, so from their standpoint, they'll never have to make a change. But in reality, we have this FFI, we have memory mapped objects, that basically make assumptions about the size of pointers. And that's in the Smalltalk code. I see it all the time, byte array, new 4. So I got to go searching around the whole image to look for, instances of 4, because I know that someone's assumed a 32-bit address. And so it kind of goes like that. It's unfortunate, but, So there are code changes to the image, but hopefully, and for most users, from most users' perspective, it won't be noticeable. So we've got these platform functions, the way we make these callouts, they're now dynamically sizable. These OS structures, they're dynamically sizable. They kind of have this little teeny C compiler front end thing that kind of tracks knows the ABI rules of the platform. So here's just a quick example. In Win32, we've got specification for pack 1 byte boundary. We've got this struct, which has some fields, and then it's only pack 1 if it's Win32, not 64-bit. And so now what we have is kind of, here we're defining the structure with its members, and its types are pointer, uint32. And then we can say something like, okay, and if it's not a 64-bit VM, update the alignment type. So internally, it computes the field offsets for the given platform. So now at the bottom here, it shows you kind of the new way you just access a field. This is the symbolic access. You just give it the name of the field. Before, it was up to you to compute the actual offset number, which all sorts of things are hidden in that number. Padding, alignments, all the various, issues, which was very difficult, made it very difficult to do a binding. So we're now describing anonymous unions and structs. You don't have to define them in the same order. There's an internal dependency resolver which will handle, because structs can refer to other structs nested, and so it kind of handles all that. 64-bit VM is just a recompile. So we don't have a separate 32 64-bit image converter. It's kind of on the fly, as we were saying. We're talking about 80% in the current VM, a little bit faster on 64-bit, but we can't really compare it to anything previous. And user code, as we were saying, is largely not aware of the changes that we've been making. So we've got, we've got some stuff left to do. We've got our JIT, which is our first level JIT at least. Which is 90% complete. It's based on LLVM, and we've still got to do a 64-bit packager, garbage collection improvements, performance tuning, various things like that. So there's, if you need more information, I'm sure these slides will be up. And so before we complete, I'll just try to show, because I think I'm kind of running out of time, but I got actually just a couple of minutes. What I'm going to show is I'm just going to bring up a 32-bit image that I'm just going to save into a 64-bit folder and then just launch it with the 64-bit VM. So here's a 32-bit image, kind of showing. I put up some workspaces. I'll just bring up a quick game, just something interesting to save off instead of just an empty-looking image. So let's take the game view, and I'll just play just a little bit to add some state to the board. Let's do that. Okay, so then we'll do something like that. Pause it. Just leave it there. And then I'm going to go ahead and save this image, and I'm going to put it in the place where the 64-bit VM is located on my machine. Right there. Okay, so I'll go ahead and close this out, and then for the final step, I'll just, and this is going to take a moment. Oops. So what's happening here right now, it's going to take a moment to launch, and what's essentially happening is it's loading up the image, and as it loads it up, it takes each memory segment, and it converts it to 64-bit. Byte codes are being converted. Various other parts of the loader, tasks of the loader are actually converting it. It's going to rise a lot in memory, and then it's just going to dump it all after it loads up. So I'm just kind of looking here because I know when it is roughly complete. And so hopefully what's going to happen is it's going to bring up the 64-bit converted image, which will be where we left it. And then all you need to do is you just need to save the image, and then you'll have your 64-bit image. Now it's taking a little bit longer than normal because all of our internal ICs are still in 32-bit format. So every time we launch the 64-bit VM, we're still paying that penalty. So in a real production environment, we would have converted those. So it's come up now. So now this is converted to 64-bit. So you can just, it just continues kind of where it left off. And so now if we ask this, let me see if I can make this a little bit larger. Oops. Forget my own shortcuts that I add. Okay. Control plus. So now if we have a bunch of these new APIs that, as I was saying, because the image is not transparent, 64-bit, sometimes you need these APIs, you need to reflect on them and make decisions one way or the other. And so we've added a lot of new APIs to do that. So pointer size here should be 8, not 4, and on we go. So we hope this is a good estimate of what the transition will look like for our customers. The reality is that there will be customers who have done things like created their own bindings, which will need the OS structure enhancements we did to make sure that it's compatible. But if they've stuck with kind of the non-native stuff, this is exactly what it should look like for them. And that's the end of the talk. Did anybody have any questions? Andre? I think one up here. Yes.
I wanted to ask if you agree with the step-by-step approach.
Uh-huh.
But I wanted to know if it's in your plans, even far away, since now you do have a 64-bit representation, you're planning to take advantage and refactor the object layout, for the pointer, to use some immediate objects, which are then some bits for tagging and web object like small dollar,
Yeah, I didn't really talk about these enhancements, but are you talking about like large, small integers and yeah, that's part of the rollout is the larger, small integer support, immediate floats. Some of these things that we've changed our header around just a little bit so that it's not so big. We actually don't have it in quite yet, but yeah, I mean we've roughly looked how to do it. I mean. The headers have kind of been what we focused on to keep that nice and trim, and it's fairly trim, but we have more. Yeah, that optimization phase is still. That's kind of why we put 80% done and 80% left to do is kind of that whole stuff. But yeah, it's good question.
What does your LVM-based chip look like? How good is it?
Well, the expert on that is not here. He'd be better to talk about it. But I guess, it's been the same, like in what aspect? As a native code generator, what specifically?
What does it look like? Like in what way LVM plays a part
Yeah, so LVM is we've written a native code generator using the LVM C++ API. It generates I know you know this, but for some other, it generates the IR code, intermediate IR code, and that gets pushed down to the various platform architectures. And so we're kind of just finishing that up, and larger memory at the moment. We see some, it's a large thing to link to. It takes longer to do the code gen without some special hacks. So it may end up being kind of what a lot of other folks do, and that is being kind of the hotspotted gen, hotspot JIT. We'll have something in between that's a little bit faster. And but we're still, I don't know if I can answer with good, because the guy who's really good at it is not here. I don't know as much about it. I see the code as it rolls in. We still get that nice incremental development going. But I've yet to, once we finish, I'm looking forward to all the benchmarking and really getting my hands in there and seeing what it can do. But we're excited about it because, again, it's within our goals of wanting to have kind of cross-platform code gen. That part's really cool. We just hope that the memory requirements and the native compiled time, we can get that under control. I know that's always an issue for folks that use it. So we're cautiously optimistic, I'll say. Yes?
So what's the impact on the Smalltalk bytecode? Do you have new Smalltalk bytecode?
Yeah, so we've...
More expressive bytecode?
Yeah, we've gone... we have a bytecode set that is the same for 32 or 64-bit. So we're kind of moving to that. It's not more expressive. It's roughly the same. It just uses offsets a little bit differently. It's more indexed based than it is offset based, because that would have to change across, you'd have to carry 2 bytecode sets if you were to do that. So yeah, we've unified them, but I wouldn't say the semantics have really changed all that much. Yeah. Any other questions? Well, thank you very much. Appreciate your time.